In the last video, I conducted this experiment of dropping a golf ball. Let us first understand what happens due to this collision as far as the materials are concerned. When a ball is dropped from a certain height on a hard surface, it carries energy which is equal to the potential energy of the ball before it was dropped. The potential energy is mgh, where m is the mass of the ball, g is the gravitational acceleration, and h is the height. The potential energy is converted into kinetic energy as the ball travels the distance. Just before the contact, it will have kinetic energy which is equal to half mv square. All of the potential energy has been converted into kinetic energy. Now this ball will rebound or bounce back after hitting the flat hard surface. Rebound will depend upon the properties of the materials of the ball and the surface. Let us draw the ball in bigger size. If the contact is perfectly elastic, then all the energy will be transferred back into the ball after the collision, which comes from the conservation of momentum principle. In this case, the ball will bounce back to the same height. It will reach back the exact location from where it was dropped from. If either of the materials is not perfectly elastic or viscoelastic, then the energy will not be conserved. There will be loss of energy during the collision. As soon as the ball hits the surface, it will deform elastically. This deformation is causing the ball to dissipate energy. This energy has two parts. The first part is the elastic energy storage, which is stored in the ball. The second part is the viscous loss, which is consumed during the deformation of the material as viscous loss. The viscous loss energy is lost and cannot be regained, but the elastic storage energy as a result of strain in the ball will be regained. Therefore, for a contact where either the ball or the surface is viscoelastic in behavior, during bouncing back, the ball will not regain the same height. This height loss represents the energy loss due to the viscous nature of the materials. And this represents the purely elastic strain energy stored in the material. This concept of the stored elastic strain energy and the energy loss can be used for dynamic loading where the stress is changing in sinusoidal manner. In the following, we will apply this concept and calculate a ratio of the energy that is lost to the maximum stored energy. Previously, we wrote the equation for stress and strain in a dynamic loading case as So epsilon is equal to epsilon naught sine omega t, and for stress we wrote sigma naught sine omega t plus delta. So delta is the phase lag, so this kind of equation will have at time t equal to 0 the strain will be 0. If we want maximum strain at t equal to 0, then in that case we can write the equation for dynamic loading as this. So either it can be written as in this format with sine omega t, or we can write in terms of cos omega t. Now the stress function in dynamic loading can also be written in the form of complex quantity as is done in harmonic systems. So for example, the stress can be given in this format where the complex stress is given as the real part and the imaginary part. So here sigma star is the complex stress. It contains the real part and the imaginary part. So stress follows in this way, and here again I is under root minus 1. So in this situation the phase lag delta can be given by this equation, and the storage and loss modulus can be defined by the E1 is the storage modulus. It is given by the sigma naught prime divided by epsilon naught, and E2 is the loss modulus, which is given by sigma double prime over epsilon naught. So this is another way of writing the stress equation and defining the storage modulus and loss modulus. Now the stress and strain function can also be defined by an exponential type of equation, because in many applications we may require this type of equation, and therefore we should understand that the same dynamic loading can also be given by this equation. So here sigma is equal to sigma naught star, so this is a complex stress, and exponential I omega t plus delta. So again I is minus 1 under root minus 1. So here delta is the phase lag, and the strain will be defined by this equation. So by using a combination of these two for the stress and strain, as well we can define the dynamic loading of viscoelastic materials. So here in this case this equation is possible because of e to the power I theta, and e to the power I theta is given by this equation, which is also known as Euler's equation. So e to the power I theta is equal to cos theta plus I sin theta. And if you look at the graphical representation of Euler's equation, it is given by these two. So this gives the real part and this gives the imaginary part. So the real part comes from cos theta, and the imaginary part comes from I sin theta here. So by using an exponential equation like this, it is possible to define the dynamic loading
it is possible to define the stress and strain in dynamic loading, and we can analyze the viscoelastic behavior of polymers. Now in this part we will try to find out a relationship, a ratio of
energy loss
over the energy stored. So first let us calculate energy dissipated per cycle, delta E. So delta E will be given as integral of stress and delta epsilon. So this is the strain part. So this comes from the stress strain curve, for example, stress and strain. So this is the element of small element of strain, and this is integrated over one cycle. So the loss energy dissipated per cycle is given by this equation, and further we can say that this integral is has limits of from 0 to 2 pi over omega. 2 pi over omega is one cycle. And for d epsilon, we can write d epsilon upon dt multiplied by dt. So here t represents time. Now substituting expression of sigma
from equation 3.76, epsilon equal to epsilon naught sine omega t.
So first we should find out d epsilon over dt. So we have epsilon equal to epsilon naught sine omega t. So therefore d epsilon over dt is equal to epsilon naught omega cos omega t. This will go for this substitution, and sigma has already been defined in my previous video as this. Here E1 is the storage modulus and E2 is the loss modulus. We can write delta E as so this is for sigma. So this expression is for sigma, and for d epsilon over dt we can write and then dt. So now this equation we can further write it Now this equation contains two components. One is the storage modulus, another is the loss modulus. So
the viscous loss of
energy will be calculated by this part. So we will only consider this. So here we will use a trigonometry formula which is given as so this is a formula we will use now. So only considering this part we can write now here we are replacing cos square omega t by this term. So now we will integrate this one with the limits of 0 to 2 pi over omega. Now if we substitute the limits to this, then we can get 2 pi over omega minus 0 for t plus 1 over 2 omega sine 2 omega, and t will be 2 pi over omega minus sine of 0. So this becomes 2 pi over omega plus 0. So therefore we can write delta E as omega epsilon naught square E2 over 2 multiplied by 2 pi over omega. This is finally we get delta E is equal to pi E2 epsilon naught square. So this is how we can solve this integral, and finally we get this one.
this is the energy loss in one cycle.
In the cyclic process for one cycle. Now we want to know the energy storage, how much energy is stored. So the energy is stored, the maximum energy storage will be when the cycle is only quarter. considering this cycle, for example, so this is a complete cycle, so this is a quarter of the cycle, so 1 quarter, 2nd quarter, 3rd quarter, and the 4th quarter. So considering only the 1st quarter, this gives the maximum strain storage. So therefore we will use the limit of only for 1 quarter. So integrating delta E over 1 quarter of a cycle will give the maximum stored elastic energy. So this will be given as this one, integrating delta E from 0 to pi over 2 omega. So pi over 2 omega is 1 quarter of a circle of a cycle. Now for the energy storage, we will use the first term, this one, because this is the storage modulus and this is the real part. So we will write same equation here, E1 omega epsilon naught square sine omega t cos omega t dt. So now again we will integrate this equation to find out what will be the E, value of E. So let us integrate this. E is equal to E1 omega epsilon naught square 0 to pi over 2 omega sine omega t cos omega t dt. Now again we will use a trigonometric formula which says sine omega t cos omega t is equal to half sine 2 omega t. So we will substitute this in this integral here. Half sine 2 omega t dt. So we have simply substituted this with this. So now we will put these limits to cos 2 omega t. First pi over 2 omega, which will give us cos pi minus 0, cos 0. And this will be minus 1 and minus 1. So this becomes minus 2. So 2 and 2 gets cancelled out, negative gets cancelled out, omega gets cancelled out. So now we have got the final equation as half E1 epsilon naught square. So this is the energy storage, the maximum energy storage in the system. So we write the equation for maximum stored elastic energy as this one. So now using our equation, previous equation, which says tan delta is equal to E2 over E1, and if we write E2 and E1, so just now we have found that delta E is equal to pi E2 epsilon naught square, and E as half E1 epsilon naught square. So if we use these two equations, we can find out that E2 over E1 is actually delta E over 2 pi E. So this ratio is known as specific loss, so which is also equal to tan delta 2 pi. So the specific loss delta E over E is given by 2 pi tan delta. So this gives us the ratio between the energy loss in one cycle over the maximum energy storage.
In this module, we learned that the dynamic loading, stress and strain harmonic equations can also be written in other forms, including the exponential form. The ratio of the energy loss in one cycle to the maximum energy storage is given as 2 pi tan delta, where delta is the phase lag between the stress and the strain profiles of the dynamic loading.